general relativity, step by step. I've been trying to come up with an equation of state, a link between pressure and density for the universe. And I've reduced it down to this rather fearsome and difficult looking expression here. What I'm going to do in this screencast is expand the two summations, this summation here and this summation here. And it's always as well to write down the squared line element, dt squared, plus a squared dr squared plus q squared d theta squared plus sine squared theta d phi squared. Actually, it's as well to write it out in its component form. 0, that'll be a squared. 0, 0, that's a squared q squared, 0, 0, 0, and that's a squared q squared sine squared theta, tr theta phi. Okay, so now we're in a position to do our expansion. So it's stress energy tensor with one upstairs and one downstairs index by dt. Plus, and now I'll actually do the summation, and the summation is over this character nu here, which has got four possible values. It can be t, r, theta and phi. So I'm just going to write them out, put it in brackets. Christoffel symbol t plus, and then the nu equals r here, so it's r. There's quite a lot going on here. I know I can write it out a little bit more efficiently if I factorize it, but I'm not going to do that. I'll do it in the next step. We've done the t, we've done the r, we've done the theta. So here nu equals theta, which is the third one, first, second, third term here. T plus the final one, which is phi t phi, stress energy tt. Okay, that's that term done there. Tick. Back to black. Okay, and now this is a little bit more well, it's not more complicated. It's still a summation over 4 minus, let's just write it out, summed over pi. So it's t plus, and then pi equals r t r pi equals theta now, t theta, pi equals theta, plus Christoffel symbol phi t phi, phi. It's a characteristic feature of this kind of work that just as you get used to what's going on, and you can do it sort of automatically, just as you get enough practice with the summation, then it finishes, because you've only got 4 to think about. We can make a little bit more simplifications just by observing that that cancels with that, because they're the same term. But now we've got an irreducible set of things to evaluate. We have got to evaluate 1, 2, 3 different Christoffel tensors here. No, the Christoffel symbol is not a tensor. I'll say again that I might have done this absent-mindedly. If I write down a symbol, a Christoffel symbol, sometimes I'll write it down with this curly bracket notation. That's a very old-fashioned notation, simply because the first book on tensor calculus I ever got and I ever read was incredibly old. Murray R. Spiegel, it was called, Tensor Calculus. An excellent book. Anyway, that's a very old notation, and this is a new one. So what I'm going to do is I'm going to evaluate these 3 Christoffel symbols, and I'm going to do that now. Let me just remind myself what the Christoffel symbol is. Christoffel symbol we call alpha beta gamma equals 1/2 g alpha delta di g di x. I'll put the skeleton in first as ever, plus di g di x minus di g by di x, and now I'll fill in the gaps. The delta is the summation variable which sums on the first, the second and the denominator. What have we got left? We've got a beta and a gamma which must go there. Beta and gamma goes the other way around here, and they go together there. Okay, well that's great. Now what I want to do is to evaluate the three Christoffel symbols that I need, and we'll start. We don't need the TTT one because they cancelled out. It's not very difficult anyway, but there's no point doing things that we don't need to do. Let me just get rid of that. So what I'm going to do is I'm going to work out, I'll do them all in sequence, R, T, R. And that means we have got alpha, we've got beta, we've got gamma, and we've got delta. So I'm just going to pick off there. This alpha is now equal to R. What's the beta? The beta is equal to T. Gamma equals R. Now delta is actually summed over. There's a summation over delta because it's written in the upstairs position and the downstairs. Upstairs, downstairs, upstairs, downstairs. But in this case we know that it must be equal to delta because we've taken a great deal of difficulty, taken a great deal of trouble to make our metric tensor diagonal. Look, the only non-zero terms are on the diagonal. So that makes our life a whole bunch easier. So that requires that alpha equals delta, so delta must equal R. Actually, I'll do the others in the same format and I'll do them one at a time. What's next? We've got T, we've got R, we've got theta, and we've got phi. So the next one's going to be theta, T, theta, and the next one is going to be phi, T, phi. So we've got alpha, beta, gamma, and delta. Now alpha equals theta, so that forces delta to equal theta as well because of the diagonality constraints. And beta and gamma are T and theta. So you can see that the beta argument stays as it is, as a T, and we're changing all the other three from R, theta, and of course this one is going to be phi now. Alpha, beta, gamma, delta, phi, beta stays as T, phi, and phi. Okay, and I can get rid of that. So I can just evaluate these things. So that equals 1/2 G alpha delta. So it's superscript RR times di G delta beta is RT, and it doesn't matter what it's differentiated with respect to because my metric tensor is diagonal. So it doesn't matter what I'm differentiating with. I can't even be bothered to write it out. What's this one? Gamma delta. Gamma delta, so it's G subscript RR by di T minus, I don't want to evaluate it just yet. I want to look at the third term here because quite often they cancel out identically. So it's di beta gamma. Beta gamma. No, it's an RT term, which again I can ignore. Which equals 1/2 GRR di GRR by di T. I want to say again, this is not a formal tensor equation, so there is no summation. That R refers to that index there. It's not a generic term, it's just an index. Equals, well, let me just remind myself what my metric tensor was. With downstairs indices, it was this guy here, and to evaluate the metric tensor with upstairs indices, we need to take the matrix inverse of it, which is, because it's diagonal, that's easy, it's just 1/a squared. So it's 1/2 a to the minus 2 di a squared, because that was the term in the metric tensor, by di T, which is nice, a dot over a. Dead easy. Dead easy. Right, let's do the next term. Whew. Equals 1/2 G alpha equals delta equals what? Alpha equals delta equals theta di G. Now then, delta beta is theta T, and again by di something, I don't care, we can just ignore it, plus di G gamma delta is theta by di beta, which is T, minus di G beta. You see here, beta gamma is beta gamma. Beta is T, beta is t, so it's t theta, off diagonal, 0, don't care, equals 1/2 g superscript theta theta di g downstairs theta theta by di t equals what? 1/2 times the theta theta superscript position is this one here, and because it's diagonal it's dead easy, it's 1 over a squared q squared, 1 over a squared q squared times di by di t of a squared q squared, I guess, because that was the term we're interested in, which equals, again, the differential, the q's cancel because that's just a constant. It's just a constant in terms of time. Of course, q equals q of r, so there's no time dependence there. So again, that comes out to be a dot over a. Well, that's quite nice. And now we'll do the final term, 1/2 g. Well, we can just write it down 5 because wherever we wrote a theta down here, the thetas all turn to phi's. So it's di g phi t by don't care plus di g phi by di t minus di g t phi by di g something by di don't care equals, and this is getting easy now, g phi di g subscript phi by di t equals 1/2, the half being from the definition of the Christoffel symbol, 1 over a squared q squared sine squared theta di by di t of a squared q squared sine squared theta. Everything apart from the a cancels, and that's going to be again a dot over a. Whew, well, that's nice. So the three things that we needed to identify, I'm going to circle them in orange, this one, and this one, are all the same. And that's quite a profound observation. They're all the same, and I don't have a good explanation for that, other than it is a reflection of not quite the symmetry of the coordinate system we've chosen, but it's a reflection of the simplicity of it, really. We'll see how it works out. We'll see how it works on. This is going on too long. I've already talked too long. It's 12 minutes. I'm going to stop here, and what I'm going to do in the next screencast, now that I've got my I won't pinch in. Now that I've got my expression, now that I've got my expression here, the hard bit was evaluating the Christoffel symbols, which I've done here in these orange circles, and I'll do that in the next screencast. Stop there. Stop.